Welcome to the Lila and Bob Loewy lecture. So just a few words on Bob Loewy. Bob Loewy was a graduate of Rensselaer. He was from the class of 1947. He's had a very long career. Several of the early years was spent in the companies. He was chief of dynamics at Boeing VTOL, spent a year as the chief scientist with the Air Force. He joined the RPI, joined the faculty here in 1974, and he served as a provost, and he was also the director of the Rotorcraft Center. Then after spending around 19 years here at Rensselaer, he moved to Georgia Tech, and he was the chair of the Guggenheim School from 1993 to 2008. Bob has won many, many awards, many big honors. He's a member of the National Academy and a winner of the AIAA Guggenheim Medal. Now, the Loewy, so besides being a student here, besides being a faculty here, recently Bob became a donor, and he gave a very generous gift to Rensselaer and to Georgia Tech. And the idea was that every other year, Rensselaer would hold a lecture in vertical lift, and then the other years, Georgia Tech would do the same. The Loewy lecture started in 2015, and the first lecture was given by Mr. Chris Van Buren of Sikorsky at Georgia Tech. And then in 2016, Dr. Bill Lewis, who's here with us, gave the Loewy lecture here at Rensselaer. In 2017, Susan Gorton from NASA gave the Loewy lecture again at Georgia Tech. And this year, it's my great pleasure to have Mr. Mark Moore from Uber give the Loewy lecture. So a few words about Mark. Prior to joining Uber in February of 2017, Mark spent about 32 years at NASA Langley Research Center, and he was the driving force behind Distributed Electric Propulsion at Langley Research Center. I think it all started with a very strange-looking aircraft called the Puffin. And, you look at it and you say, what is this? But it led to something else, and it led to more, and it led to more, and it led to more. So after the Puffin, Mark led some major programs, including the GL-10 Grease Lightning, the LEAPTech Mobile Rig, and most recently, the X-57. After that, Mark left to join Uber, and he continues to be a champion of basically eVTOL and on-demand transportation from his vantage point at Uber, where he continues to bring people and organizations and ideas together. He's a winner of the 2017 Vertical Flight Society Paul E. Houter Prize, and we are very pleased to have Mark with us today.
Yeah. So it's actually funny that I'm giving the Professor Loewy lecture, because I only met him once, and that was when I was doing the oral board quals at Georgia Tech for my PhD. Seems like a nice guy, right? So I get in there, and he asks me a wonderful question. It was a wonderful question because I knew what the answer was. It was one I had prepped for. And really confidently gave him the answer for 5 minutes. And then he said, literally did that. No, no, no. Start over. You got it wrong. And I'm like, hold on. I know I just gave the right answer. What the heck am I doing wrong? And he so confounded me that for the next 20 minutes, I blabbered and talked like a raving idiot and could not get through it well. So if you're ever going to go through the oral boards, watch out for that trick, because I gave the right answer right at the beginning, but he wanted to throw me off to prove that I could go back from first principles and give the answer. And he taught me a valuable lesson. You don't just spit out the answer, right? If you want people believing in you, you bring them along for the ride. You show you know what you're talking about. So what I'm going to try to do today is show you that I know what I'm talking about in terms of this awesome new on-demand aviation market and eVTOL aircraft. And I really do believe that we are at the beginning of a fantastic new age of aviation. In fact, when I grew up, by the time I was 9 years old, I knew I wanted to work for NASA. I knew I wanted to design vertical lift aircraft. That's the only thing I've ever done at NASA. And when I finally got to NASA, I'm like, oh, shoot. All the really exciting days of powered lift were in the 50s, 60s, 70s, and a little bit into the 80s. And now it's over. Nobody cares about it. And again, my whole career was just trying to prove that powered lift had a future. That this is what even Orville and Wilbur Wright wanted from the beginning, of everyday use of aviation in people's lives. And we are at this really exciting point where it could not be more exciting than we were in the early 1950s, and all the cool new Xplanes, one every year, were taking place. We are really privileged to be the generation that brings vertical flight to the masses. Couldn't be better. So again, I'm really excited. Thank you so very much for this opportunity to give this lecture. Here we go. So I called this talk the dawn of eVTOL. And that is because, again, it's a really exciting time period where in 2009, I was on the team that came up with the Green Flight Challenge. And we wanted to prove that electric aircraft could work. And very few people were we had many skeptics who were saying this is nonsense. So we created this $1.5 million prize, and in 2011, it was really exciting because the NASA Chief Technology Officer got up and said, well, I wasn't a believer in this, and we have just proven that electric aircraft are not science fiction. And the aircraft was able to fly 108 miles per hour, 200 miles, and show that there were possibilities for this new technology. And especially if you look back at aviation, propulsion technologies have always been the driving force of big change, right? When we got the turbine engine, big changes to aviation. And so it is really amazing that just in a few years, electric aviation really has become even more capable. The electric motors are advancing at an incredible pace. The batteries, the digital controllers, everything is really coming along. In fact, it's kind of funny that you had 3 aircraft back, what was it, 2015 or maybe it was 16, or maybe even 17, the 100th anniversary of flying across the English Channel. There were actually 3 aircraft that did it almost on the same day. But what's so funny is this little Cree with 2 little electric motors was able to do it before Airbus with the E-fan. And to me, that's kind of like a harbinger of how this is a disruptive market, where you're going to have these new little technologies or new little company players that come out of nowhere and surprise the big companies. So just in a few years, in fact, we've had flight around the entire globe, strictly on electricity. So this future, though, the next few years are yet to be written. And I can't wait until everybody comes out in public with the different concepts that they're doing, right, Scott? And shows the incredible things that they're working on. But very much, we at Uber are going to be a driving force to make sure this market evolves. And so we're very serious about, in 2020, that demonstrators are able to show up and prove what eVTOL aircraft are capable of in terms of performance, noise, safety, and reliability, do experimental flights, and then within the next 3 years, by the end of 2023, that we'll be able to start introducing the first eVTOL aircraft into initial commercial operations. So that's very much what we're focused on, and it's actually really important to hit this target. As I was talking to some of you, there's a lot of venture capital money that is going to play for us, and they have limited horizons. And we need to do our part, which at Uber, it's bringing this ecosystem together. It's making the different pieces come together. So while Mike talked about all these wonderful new vehicles that are being developed, we at Uber are not developing an eVTOL aircraft, and we never will develop an eVTOL aircraft. There are companies that are much better suited than us to do this. And I would like to follow on the one comment that Mike made. And that is, he kind of asked the question, okay, so here's the hype curve. Is this kind of just hype, or is this real? And from our perspective at Uber, again, we're not developing a vehicle. And you know, if you looked at any one of these smaller eVTOL companies, you could say, well, you know, their mantra is, if I build it, they will come. You know, buyers will come, the market will come. We're doing the opposite thing at Uber, and that is, we are the on-demand market. We have come, we are interested. Here's the requirements that we need for success. Bring the vehicles. So we are not just hyping the market, we are creating the market conditions and investing in the ecosystem so that all these different successful eVTOL aircraft will have a place to take off and land and to operate and carry passengers. So it's not the most exciting thing. I know from having done it, developing the vehicles is the really exciting part, but what we're doing at Uber really is a serious market commitment to bringing it about. So Mike already talked about the VTOL Wheel of Misfortune. I will just add this. You know, over my 32 years at NASA, I've studied every one of these aircraft and designed aircraft that used many similar technology sets. Only two became operational, and for a very good reason. They were mechanical, complex to the nth degree. There was so much VTOL claptrap on any one of these concepts that it seriously damaged the payload fraction, the performance, or some other really important characteristic, so you just wouldn't bother ever taking it into commercial service unless you were just desperate for that, like the military. So it really, you know, the more and more I looked at this VTOL wheel over the years, it was like, how can we get rid of this mechanical complexity? And that is the beauty of electric propulsion and distributed electric propulsion. It lets us get rid of all the claptrap, all the gearboxes, all the cross shafts, all the stuff, and replace it with a new propulsion type that has one moving part, which are bearings, which last a very, very long time, which you can sense going bad before they actually go bad. They're incredibly efficient, 2 to 3 times more efficient than turbine engines. They're incredibly compact, which make it ideal to distribute wherever you want on the airframe. So they have this wonderful characteristic of essentially scale independence, where whether it's, you know, a small 1 horsepower motor or a big 1,000 horsepower motor, both are going to be able to achieve about 95% efficiency, have a great power to weight, and be incredibly compact. So it is the first time we've had a propulsion technology that is not sensitive to scale. You try to make a small turbine, that small turbine is going to be really inefficient, isn't going to have a long TBO, and the same thing for reciprocating engines. So we have a new degree of freedom in propulsion technology to leverage, which is letting us create this new wheel of fortune. Because I'm convinced this is going to be a very healthy and vibrant market. So in terms of, again, Uber's coming at this trying to help companies develop products that meet the requirements that can make money and be successful in the market. We understand the on-demand market because we have over 10 million trips a day being performed across the world. So we understand where people are traveling, their time dependency, where the traffic is, you name it, and really understand how important it is and what an opportunity it is to go into the third degree and get above the ground gridlock that we're stuck in the cities. So, I mean, what's important to realize in terms of these mission needs for urban air mobility is they're very close proximity operations. Typically, helicopters are operating, you know, not in the urban cores, right? San Francisco, where I work, they don't let any helicopters take off and land in the city. You know, the one place where there has been a few operations is at a hospital, and San Franciscans don't even want EMS helicopters flying or landing in the city. And a lot of that is perceived safety, but also real safety. In the past, helicopters have not had the best safety record. Over the last 10 years, actually, they've gotten a lot better. But primarily, the objection is noise. You know, communities don't like having that helicopter noise. And again, the thing to realize is helicopter noise is a very low frequency, impulsive sound that will rattle these windows. And in fact, you can feel it in your chest. It is very observable, and that translates to annoyance. So we gotta, if we're gonna open this market door, we've gotta do a much better job on perceived safety and on community noise and being a good neighbor. Also, for us, for Uber to make money, we need high throughput, right? We can't be doing aircraft that are loping along at 40 miles per hour and carrying 1 or 2 people, right? That would be a low productivity solution, and airspace is a resource. And if we're clogging our channels, even though there's a lot in 3 dimensions, as we start filling it up, we don't want those pipes to have sluggish liquid going through it. We want high throughput, because that's what aviation offers, right? It offers high productivity, high speed, high throughput, and that's how you make money. So the other thing that's really important in terms of market need is we need to be operating these vehicles at high utilization to make money. Average helicopter utilization is between 300 and 600 hours per year. They're very expensive assets. That's not enough utilization to get to good economics. We need to be operating these vehicles 2,000 hours a year to make money. That's much closer to what the oil services industry does at about 1,800 hours per year. So we need these aircraft to be incredibly reliable, which again plugs into to electric motors, which have very few moving parts and high TBOs. So that also plays into the low operating cost in terms of reliability. Uber's not interested in just serving the macho elite with this market. It is about having a mass transportation solution that can serve the needs of our app customers. So it really needs to be this high reliability and drive to low operating costs. So fortunately, that maps up with a number of the advantages of eVTOL. So there really is this wonderful opportunity, and I'll say this. One of the reasons I'm most excited about eVTOL aircraft is because, again, they're going away from these mechanical systems and going to an all-digital aircraft, right? You've got the ability to mate into these autonomy technologies so that you have all digital signals all the way through to the control forces. And there is this natural harmony that could exist between the vehicle and the autonomy systems of the future as they become autonomous. In terms of noise, it's a huge advantage to not have an advancing and retreating blade. In cruise, when you're trying to go fast, that is a fundamental limit that requires single rotor helicopters to have high tip speeds so that they can cruise fast without stalling the retreating blade far out on the disc. And so being able to get to wing-borne solutions where you can talk about lift-to-drag ratios of 13 to 16, and that maps into, again, these severe energy constraints that we have with electric aircraft really well, versus being at lift-to-drag ratios of 4 to 5 with helicopters, or with quadrotors without wings, that's 1 to 2. I mean, it's startling to me that people don't talk about just how bad multi-rotors are in terms of cruise efficiency. They're great for hovering and sitting there in one place. That is the ideal mission for them. But if you want to go forward, they're not getting faster than 60 miles per hour, and that is at a lift-to-drag ratio of 1.5.
Test.
So,
1, 2, 3. Testing. 1, 2, 3, 4, 5. Testing. 1, 2, 3, 4, 5.
Someone else is using that line.
okay. So, I mean, you won't catch me putting multicopters without wings on the Uber network. It's just it's just a fundamental mismatch with where we need to be in terms of energy efficiency, speed, and overall capabilities. So in terms of the mission, again, everyone kind of talks about just how bad batteries are. That's not what is important. What's important is if they're good enough to do what we need. And if you look at these markets that we're talking about, which are in the city, we're not talking about going outside of the city, because guess what? If you look at a chart of trip density, you have this huge population that wants to take a lot of trips that are on average 23 miles. And if you try to then go out and serve the exurbs and different localities outside of that, it's diminishing rapidly. So the place to make money is in the cities, especially those that are facing gridlock already. So again, the average trips on the order of 23 miles, the longest trip that we need is 60 miles. And that actually maps in quite well to what batteries are capable of providing, as long as you're pushing that lift-to-drag ratio in cruise up to above 10, and not being below that. And not having a hovering mission, right? Helicopters will always be the best thing on the planet if all you want to do is hover. The low disk loading, you can't beat that. We're not interested in hovering. We're interested in 30 seconds of hover at the front end, at most 45 seconds on the back end to deal with the uncertainties during the approach. These are not meant to be hovering machines. They're meant to be transports. And so they just need to be able to do hover or transition for a very short period of time. But if you push to really high disk loading, for instance, like the Lilium concept, I mean, there's all sorts of problems that happen there, where high disk loading requires really high C rates in the batteries, high discharge rates. That's problematic. And so what we're about is being able to achieve essentially the 60-mile longest trip distance. But also what's actually more important is that we can fly for 3 hours during the peak in the morning and the peak in the afternoon, and at most sit on the ground for 5 minutes when we load and unload passengers and get a little bit of recharge, enough to keep us going, so that essentially we have this sawtooth distribution. We're constantly running the battery capacity down, which is the vertical axis, but we're able in that 5 minutes just to get enough charge so that we can do the next 25-mile average mission, get a little recharge, bounce the energy state back up, so that for 3 hours straight we can operate just with those 5-minute loads and unloads recharges. That's the harder mission that we're designing for. So just a little bit more of this trade-off of cruise efficiency and disk loading or hover power required. You know, you can see multicopters really inefficient at cruise, going across the horizontal axis to the right. a tilt duct with high disk loading like the Lilium concept going up to require a megawatt of power in hover. So the sweet spot is kind of in that corner, right? Which compounds have been trying to achieve for 30, 40 years. But in my perspective, you know, since the mission is just really short in terms of the hover requirement, you want to bias more towards a little bit more power and a little bit more cruise efficiency than where compounds are or have tried to get to. So it is a very challenging set of energetic constraints that exist. So again, for that 60-mile range, for an average 4-passenger vehicle plus a pilot, which tends to be about, from our different sizings, anywhere from 4,000 to 6,000 pound vehicles. Then in order to be able to do the repeatability, again, that sets essentially a constraint. And you can see that the battery size for that 4-person plus 1 pilot vehicle ends up being at least in this 160 kilowatt hour pack size, which is quite a bit bigger than where the automotive world is now, which is 100 kilowatt hours and below. So the energetics are definitely challenging, but even with the current 250 watt hour per kilogram cells, they are very close to getting what we need. The harder part is not actually the specific energy, it's that rapid recharge. And so right now the cells are just not quite good enough to do that rapid recharge unless we drastically reduce the cycle life. We'd like to have 2,000 cycles on these batteries so we can amortize them and they can be well affordable. Right now, they're in the few hundreds, on the order of 500, if we abuse these batteries with these rapid recharges, as we're talking about. So very much we need to push to chemistries and to liquid cooling systems that can get that heat out or distribute the heat or not have the heat with high resistance internals. So in terms of different concepts out there, you know, we do competitive analysis, comparative analysis across the different concepts so that we understand what's good or bad for our missions. Again, we're not designing aircraft for pleasure, but to understand the competitive landscape and what will best serve our market needs. So just a little bit about some of them that you've seen that are real vehicles. So you have the Kitty Hawk Cora, which is flying today, really has made this decision to, as a lift plus cruise, to be as dead simple as possible, right? The smart strategy in aerospace, KISS, keep it simple. No articulation, no moving parts, but the price you pay for that is lots of parasite drag. So this aircraft can go 110 miles per hour, but you know, the L over D max is much closer to 70, 80 miles per hour. And when you have a severe energy constraint, you want to be cruising at that lower speed. So a 70 to 80 mile per hour vehicle just isn't going to meet our needs. And especially trying to make money with a 2-passenger vehicle is just not the throughput that we need. So again, looking at other concepts, you have the Joby S4. Again, from public disclosures, that is actively flying. It's a full-size vehicle that has done many transitions and cruised. And they're kind of like at the opposite end of the KISS, right? They're embracing quite a bit of complexity where they have 6 tilt rotors. And you know, that's one of the things we're trying to get away from with helicopters, right? We're trying to get away from those 10-hour inspection intervals or high maintenance costs. And, you know, it's interesting as you compare these two vehicles, the Joby is very capable. It's a high-speed aircraft, no question about it, from our analysis. but they're, again, at two different ends of the extremes. And as an aircraft designer, I can tell you, the right answer is typically somewhere in the middle. And so I'm definitely looking for the concepts that can have the high reliability and low maintenance costs of a Cora, but the speed and productivity of a Joby S4. So that's my ideal world. So we're not doing this alone by any means. We're thrilled that we have partners with skin in the game, both on the technology and network side. This is just the vehicle partners that I'm showing. We have many more partners on the airspace and operations side, especially on the vehicle side. But I just want to talk a little bit about some of the things that we're doing. So I am a big believer that we're just in the first generation of distributed electric propulsion, and that most of the concepts are pretty brute force-ish. You know, they are flying Cuisinarts. They're just propellers all over the place. And I think in the future we're going to be able to do a lot better than that, but it's going to require especially the universities and the government labs and small companies being willing to invest in new technologies that especially take advantage of these electric motors and digital controllers. So one technology that we're excited to be working with the Army and UT Austin is stacked co-rotating rotors. And I say that this is an electric technology because what's really unique about it is this ability to have two independent motors that can, each one can control its own rotor, but they can be synchronized with great precision. So we can have the rotors with any azimuth separation at low speeds, at high speeds, they can keep that azimuth separation. Now, why is that interesting? Because Sikorsky and others have proven that this gets you an improvement in your figure of merit and an improvement in noise. Both they're not huge, 4 to 6% figure of merit increase, 2 to 3 dB decrease, but both are going in the same direction. And we have this ability to now stow the props because each one is driven independently by a motor and have a relatively clean interface. And in fact, if you think about it, like for the Joby S4 concept, as it's going through transition, it's doing that 90-degree rotation. So the cyclic forces, which are 10 times bigger than the normal forces in axial flow, are all being transmitted into that articulation. So it's a really complex articulation in terms of loads. What's neat about the stacked co-rotating technology is that, we can pop these motors up and with a simple cam mechanism, pop it out of a nacelle, and there's no loads on it during that articulation. The loads, cyclic loads don't start until we start rotating that rotor. So to me, it's getting, if we're going to embrace articulation, it's embracing smart articulation with very low loads on that articulation mechanism. But the most exciting thing about the stacked co-rotating technology, why I'm investing in it, or Uber's investing in it, is because as we've done acoustic studies on fixed RPM control, and I just saw you guys are doing some great work here too on the scaling of fixed RPM work, so kudos to you guys. If you've ever heard a multicopter, especially if it's in winds and it's trying to keep a hover, you'll hear because every motor's having to spin up and down an RPM. And it's actually really annoying noise, and it's hard on the motors. What's neat about this is by changing that azimuth separation, because as it's rotating around, it's precisely keeping whatever azimuth separation you command. But as these two rotors get closer and closer, they have an interference effect where it's more like the leading one is the airfoil and the trailing one is a flap. And you can actually get to higher coefficients of lift than the propeller alone. So it's neat in terms of being able to get more out of those rotors in terms of thrust, but also you can dial that by that azimuth separation. At least that's what we're trying to prove. And that means you can have constant RPM across all these different rotors, but still modulate the thrust. So that if you heard this vehicle, it would be all one steady RPM thrum in terms of noise, and the motors wouldn't be abused with this ramp up and down in loads. So there's so many different factors that are coming into play that make this a really cool technology for us to explore, to try to find that middle ground of low articulation complexity, but nice clean aerodynamics for cruise efficiency. So we're really excited about the Army and UT partnership. Here you see, again, we're never going to build this vehicle. We're showing this as a vision concept that could utilize this stacked co-rotating technology. Again, not counter-rotating, but co-rotating. All right, so I'm going way too long because I'm too excited about the different things. I just wanted to mention briefly, we're getting into really tightly coupled aeropropulsive problems here, and that really demands great new tool sets or applications of tools that have been developed in new ways. And so a lot of what we're doing is, especially with our partners, is trying to advance the tools and prove out across the variable fidelity tool sets from charm to overflow and power flow and vortex particle codes, everything in between, you know, how we can do rapid design or how we can help them do rapid design by proving out the lower fidelity tool sets. And we're focusing on one specific area, and that is acoustics. They're designing the vehicles. They're the experts at designing the vehicles. But not enough attention has been put into achieving great acoustic signatures and low community noise. So we think that's a key differentiator that we want to enable our partners to be the best on the planet at, because we know that that is going to be the challenge for us to get into the market with these services as we talk communities into having skyports very, very close to where they live and work. So by far, you know, as you see us develop these different concepts, they're nothing more than the equivalent of concept cars. They're never going to go into production. But speaking of production, we've got to realize that these vehicles need to be designed to achieve production rates that haven't been seen since World War II. You know, we need thousands of each one of these aircraft being manufactured per year. And in a relative few years, we see the need for 10,000 units per year being produced for our needs. So we think that there's this natural blending of the automotive and aerospace markets that needs to occur, and we're trying to help facilitate that, again, with and through our partners. So again, there's so much interesting variable fidelity tool work to do and to talk about, and again, we're excited that we're doing some of that work with the Army, as they have an incredible expertise that, especially in this area of close coupling aeropropulsive problems. So just a little bit about our 5 partners. Each one is, you'll notice, developing a completely different aircraft. Again, with the Bell, you have to decipher exactly what that is, at least until the near future. But I mean, it is amazing. Each one of these companies, right? These are Bell. They've developed more vertical flight systems than anyone on the planet. And then you see Karam and Aurora and Embraer, serious aircraft companies. Every company is doing something completely different. Is that crazy? Is this not the Wright brothers era when you see that? Otherwise, every single one of these aircraft would look identical, and the only differentiation would be some magic in the internals, right? So we are in the wild, wild west, and it's so exciting. So I'm just going to end. I've talked only about the vehicles because I'm a vehicle guy, but the feasibility of this market is not just about the vehicles. It's about this whole ecosystem coming together. And this ecosystem has to be designed for the masses. Again, we have 10 million riders a day at Uber. And we're growing somewhere between 70% and 120% per year. So we've got a lot of customers that are ready to ride in your vehicles. We just need to put all the different pieces together. So part of that is the infrastructure. So I just wanted to end just showing you some of the previews for the infrastructure. So our challenge is, right, we can't build runways in the middle of cities. That's why we're doing VTOL. But we need to be able to get this high throughput. So essentially we're designing for like several different sizes, right? Some places need more people in terms of throughput than others. Downtown LA needs to be able to handle, have several vertiports that can each handle 1,000 people per hour or 1,000 aircraft per hour, while some other nodes are going to be smaller. Well, you know, we have a crawl, walk, run strategy. So in the beginning, we're going to adapt elevated parking garages and take advantage of that top deck in order to put several different pads. You'll notice that we tend to do this layering effect where we can have essentially storage for the vehicles and emergency landing pads also embedded into the design. But as I show you several different solutions, because we invited some of the top architectural firms to actually ideate with us and develop different skyports, you'll notice that each of them tends to be elevated above the ground to help get that noise signature away from people on the ground, but also be co-located with ground transportation, roads, major thoroughfares. And that's both because we need to be multimodal, we need to connect into other ground transportations, and because we want to take advantage of the noise that those cars already make, and ideally even blend into that signature and design these aircraft to have the same signature as those highways. And that's one of the reasons why we've already collected about 6 months worth of highway data at different potential vertiport locations there, so that we can see exactly what that spectra look like and figure out how we can help our partners design to map in and hide within that noise band that already exists. So many different ideas for what vertiports will look like. I'm excited that, Mike mentioned ASTM. We're developing a vertiport standard, which is a bit different than the heliport standard that was developed previously by the FAA. And it's interesting to note, before it was just the FAA that developed that heliport standard. Now we're actually doing it in a consensus-based way so that many more voices can have an input to what those standards actually are. So I'm really jazzed that consensus-based standards are being supported by the FAA, and that's why Part 23 is going to be the mechanism for these aircraft to be certified in the near term. So lots of wild ideas by the different architectural firms on how we can get to very, very high throughput and have a compact signature in the urban core. So one last thing, my last slide, I'll just say it's not just about moving people around. We've announced that we're developing an Ubereats drone. Ubereats is growing even faster than our ground service at insane rates, and it's over $7 billion a year in revenue for us. So what better mission for drones than delivering food? And this goes back to Pete's comment, right? It's all about reach. And he talked about the golden hour. Well, we've got the delicious 10 minutes instead of the golden hour. And that is, if your French fries are more than 10 minutes old, no matter what your packaging is, they get soggy and gross. So drones give us this ability to have greater reach, so that each one of our restaurant partners, instead of only being able to serve a 2.5 mile distance away, actually I think it's 1.5 miles radius. Now as we can increase that to 5 or 10 miles, the number of customers that that one restaurant can serve is the square of that difference. So with an Ubereats drone, we can easily get to somewhere between 10 to 100 times more customers per restaurant. So that's a really exciting value proposition. There's a lot of things for us to work out, and that's why I'll just say I've talked about the infrastructure and the vehicles. The most important thing that Uber is doing is airspace. That's where we're spending our vast majority of funding on this, because you can't separate the network efficiency of requesting a ride and the airspace management to make sure you can fulfill that ride. So I know I've gone long. I don't know if there's time to have any questions, but I thank you so much for your time and attention, and would love to answer any questions that you have.
Just put up your hand if you have a question, and we'll bring the microphone to you.
Thank you for that. Carville Chalk with the Army at the Aviation Development Director at Huntsville. So the current construct for Uber relies on, if you will, a intrinsically trained workforce to operate the vehicles, right? You mentioned somewhere upwards of thousands of or 10,000 units per year in terms of the vehicle manufacturing. What would be your comment back on the training requirements? Most of the concepts you mentioned had a pilot plus passengers. So where does autonomy fit in, and how do you elevate the training, right, into this concept to account for that volume?
Yeah, so how are we going to deal with pilots and pilot training? It's a great question. So we do have actually a very specific market curve that we've targeted, which is penetration of markets, how many vehicles, et cetera. By the end of 2023, the idea is to start with 50 aircraft across 3 markets and prove out the operations, prove out the vehicles with commercial pilots. Over the next year or so after that, our goal is to get to 300 aircraft per market, again with commercial pilots. So you're talking about on the order of 1,000 pilots in that 2025 timeframe across the 3 different cities. Well, 1,000 pilots at any one time, times 2, because you need at least 2 8-hour shifts plus something on top of that as reserves. So 2,500 pilots. What's really neat is as we do that and potentially grow in those cities maybe to 500, 600 aircraft per market. If we do that from 2025 until 2024 to 2027, then we hit a really interesting number, because each one of those aircraft, well, I'm going to let you do the math, but essentially we end up with over 10 million flights within just a couple of years. And I think by the end of 2027, it's even approaching like the 100 million number. And so what we're convinced is that the FAA needs statistical proof for autonomy in order to certify it. So the idea is that we build in as much of it as we can in the background to reduce pilot workload, but then we are reliant on essentially somewhere between 3,000 to 5,000 commercial pilots until we can have statistical proof of safety. Now, in that period, we're also going to be working with Gamma and all the avionics manufacturers to try to insert what's called simplified vehicle operations. That as we prove out this background autonomy, that it can supplant more and more of what the pilot is responsible for, right? Because the pilot's responsible for like 10 different things, whether that's navigation, communication, etc. Well, very quickly, right, the computer can be proven to be a better navigator than a pilot. Not as good at communicating and interpreting and speaking, but the idea is to essentially let a simplified vehicle operation certificate be possible so that we could then bring in, I won't say lesser qualified pilots, but fixed wing pilots who are more plentiful and operate these vehicles under the Simplified Vehicle Operation Certificate. Because again, this is just flight path controlled instead of an unstable vehicle with cyclic and collective in terms of the interface. So yeah, we need somewhere of several thousand pilots, but we hope that, as we're working with the FAA, Gamma, and all the different avionics companies and manufacturers, that vehicle manufacturers, that we're able to quickly insert this SVO certificate to let us not require so many commercial rated pilots, because they are, from the oil services, they're expensive. And that's counted in our model. They're $100,000 to $125,000 per year, while you can get fixed wing pilots with relatively, with lower time at a much, much lower cost, on the order of $50,000. Did that satisfy your question? Yes, sir. Thank you.
I have kind of two questions. One, you've been asked before, but I forgot what your answer was, and I'm sure it'll be enlightening. And it really relates to safety. And I know you've been asked this before, but I really would like to hear your answer again. We have a pretty good record in helicopters, and certainly I'm pretty proud of Sikorsky's record. Arguably, I think Dave might argue, but I think it's one of the best in the world. And when you start putting this number of aircraft up, with this number of flights, you have to think about, God forbid, how many incidents are going to occur per week. I mean it, per week.
Oh,
and
this
so
is foremost on our mind.
Yeah, I know it ought to be, because it sets an interesting requirement for the designer, for you, insofar as the redundancy management schema that one has to put into this thing, which also relates to weight and cost and insurance. And I'll say it, insurance is a major part of the commercial success in helicopters. So in free form, you understand the intent of my question.
Yeah, perhaps you could take a shot. I would love to. It's a great question. So we can't be requiring 2 pilots for the vehicle by the insurance companies and make money. That's a non-starter, and that's one of the reasons why we want to get to this SVO certificate also, to be able to have better economics. So in terms of the safety, so this is, again, should we be designing these aircraft to 10 to the -9th reliability like commercial aircraft? Well, if we do, then they're probably going to be crazy expensive, right? But we need it, because guess what? We're going to be operating these vehicles in a mass market that aviation transcends even the commercial aviation market right now. So what I would say is we need to break down that safety and not just be talking about 10 to the -9th. So I want to talk about what's different from helicopters today, because helicopters today, especially over the last 10 years, helicopters have achieved essentially general aviation-like safety numbers, which is like 10 to the -6th, I believe. Somebody knows better, they can correct me. Yeah. So we need to definitely be better than 10 to the -6. Automotive cars on the ground are 10 to the -7, 8. Commercial aviation is 10 to the -9. So where's the right place to design? So we're still figuring that out, but here's what we're implementing, and that is, these are the reasons why we can be safe. One is we get to design these vehicles as a redundant propulsion control system. Helicopters don't have that. They have a single gearbox, they have many different single point failures, and they can't get around that. We can get around that, so that if any single part fails, this vehicle can be safely landed and not need to just go into auto rotation, and can maintain complete power and control and even complete the mission. So we have a big advantage on the vehicle design side. I think the simplified vehicle operations and autonomy will also be a huge player in achieving safety, because we all know, right, 70% of the fatal errors are due to pilot. And that's why we want to push this SVO, push towards autonomous as quickly as we can. But we think it's going to be probably 2027 to 2029 before we can get to autonomous operations. So those are two major things that can help. I would say the third one is this. And part of the reason why commercial aviation has such a great safety record is not because of just the aircraft, but it's because of their operations. They only operate in very specific locations with very tight control in a fleet, with fleet management. And that is exactly what we'll be doing. Helicopters,
They also operate above the weather. And
that's an advantage that they have, yes.
we don't. Seriously, we're going to have to, when I make an appointment to get to Santa Barbara
Agreed.
from Irvine,
Right.
I want to make it if it's raining or if it's...
Agreed. But we're not, so we're doing VFR operations until autonomous vehicle operations can be certified. So we're not even doing IFR. Fortunately, we have a ground fleet as a backup so that in bad weather days, we can still provide an alternative transportation solution. There's something really important I wanted to say about this. I'll just say, again, from an operations perspective, we have a huge advantage. And that is you as a helicopter manufacturer, well, less Sikorsky and more Bell, you have operators that are essentially doing who knows what with those vehicles, right? We have a huge advantage that we're going to fleet maintain these vehicles. We're going to have precise control over when they deploy and be able to know that the battery is in a healthy state and ready to deploy. These vehicles will not be landing in fields and kicking up FOD that's doing who knows what. These vehicles will only operate from skyport locations that are well managed and well controlled. So I would say, if you want to achieve great safety, the number one thing to do is to have fleet maintenance and fleet control and only operate these vehicles from very specific conditions. And that is why we'll be able to push towards commercial safety, is because of the operational construct that these vehicles are operating within. Does that satisfy you? We'll see, right?
Yeah, he asked me whether I was satisfied. So I simply, since he's invited a response, I'll give it to him.
Mark, you should know better.
All I'm
I like
saying,
dialogue.
all I'm saying is that I do like your learning from those early city experiences. Very carefully doing that. But I would set the bar a little bit higher, at least 10 to the minus 7th.
So
For the first generation one, what I'd be concerned about is public acceptance. You know, I lived through the Pan Am building experience. I don't want you to do that.
we don't want to either. We agree. Do we need to cut it off? I've gone way long and I don't want to take anyone else's time. Okay, thank you so much.